Hi, everybody. We're going to keep going with gas law notes. All right, so this is where we stopped last class. All right, so the last thing we were dealing with this ideal gas law. We had PV equals nRT, and P was our pressure, V was volume in liters, N is moles, R is our universal gas constant, and T is temperature, and it's got to be in Kelvin. Right, so what I'm going to do in this video is I just want to do a few examples of these, and yeah, that's all we'll be doing for today. So let's try a couple things. What is the volume of 1.00 moles of chlorine at STP, standard temperature and pressure? Well, if we use PV equals nRT, so our pressure is standard pressure, 1.00 atmospheres. Okay, we're trying to figure out our volume. Okay. We have 1.00 moles of the gas. Okay. I picked atmospheres, so I have to pick the corresponding gas constant, which is 0.08206 liter dot atmospheres mole dot K. And we have to be in Kelvin. The standard temperature is 273 K. So when we do this whole thing, you should come up with a number that you recognize. Our volume would be 22.40 liters. 1 mole of a gas at STP will always have a volume of 22.40 liters. Okay, we can use this relationship. What if we have 2 moles? Well, its volume would be 44.80 liters. Okay. Half mole. Well, it would have 11.20 liters. Right, so you can use this, as long as you're at STP, okay, this is just another shortcut that you can use. All right. So there are really 2 ways to use the ideal gas law. The first way is if you're given 3 out of the 4 variables and you can just solve. Okay, so this one you're just kind of plugging and playing. So let's go ahead and try one of these, or a couple of, yeah, let's try one of these. All right, so let's say a 6.75 mole sample of gas has a pressure of 2.73 atmospheres and a temperature of 63.4 degrees C. What is the volume? Now, realize that we have lots and lots of equations now. Okay, we have Boyle's law, P1V1 equals P2V2. Okay, there's Charles' law, Guy-Lussac's law. There's the combined gas law, P1V1 over T1 equals P2V2 over T2. And then finally, we have this combined gas law, or excuse me, the ideal gas law, PV equals nRT. All right, and you're just going to have to figure out which one to use. So in this case, okay, we've got moles, atmospheres, temperatures. All right, this is a typical PV equals nRT problem. Okay, and we're calculating for volume again. So our pressure is 6.75. No, I lied. It's 2.73 atmospheres. We're trying to find volume. We have 6.75 moles. Now, our gas constant, okay, there are three choices. Okay, your pressure is the one that determines which gas constant we use. All right, so we're in atmospheres, so we're going to use 0.08206 liter dot atmospheres moles dot K. And then my temperature is given as 63.4 degrees C. It's got to be in Kelvin. Okay, so we're going to take our 63.4, add 273, and we get 336.4 K. Right. Now, if you don't change to Kelvin, you're going to get a wrong answer. All right, so when we do this math, our volume would be 68.3 liters. Pretty simple. All right, well, there's a second way that we can use this gas law. So in the second way, what we're doing is we're going to be taking a gas under specific conditions and changing to new or final conditions. To solve these, we're going to use a ratio of the ideal gas law equation. So we're going to use initial over final. Our initial conditions over final conditions. In other words, I really mean this. P initial, V initial equals moles initial times R times temperature initial all over P final, V final equals N final, R T final. In other words, what we'll be having is we'll have P initial, V initial all over P final, V final equals N initial, R T initial all over N final, R T final. Okay, so we can use this relationship. All right, so let's try it. A gas occupies 250 milliliters and its pressure is 550 millimeters of mercury at 25 degrees C. Part A. If the gas expanded to 450.0 or point milliliters, what is the pressure? There are actually lots of ways to do this problem. Okay, one of the ways is using this relationship. Oops, R T initial all over N final R T final. Now, so in this case, we are changing our volume. Okay, so what we're changing from V initial to V final, is our volume. The number of moles isn't going to change. The gas cons doesn't change, and T doesn't change, right? So if we look at this and this are the same. So if these two numbers are the same, that means this whole thing, this has to equal 1. So that means PI VI over PF VF equals 1. Okay, so now you can just substitute 500 millimeters of mercury times 250 milliliters P final over 450 milliliters. That whole thing equals 1. So when I do this math, P final equals 306 millimeters of mercury. Now, a couple things that I didn't do that I want to quick talk about. First of all, I didn't convert to liters. Okay, and I didn't need to. I could have, it didn't matter, right? But because I didn't need this universal gas constant in the calculations, it didn't really matter, and the units just cancel out anyways. Okay, so that's one thing. Let's focus on this again. What equation is this really? This is really Boyle's. Right, so if I multiply both sides by PF-VF, okay, I end up with P initial V initial equals P final V final. So really, all I've done is I've used Boyle's law. That's what I did here, right? But I just set up a ratio, right? And it's actually pretty handy to use sometimes. All right, let's do a B part of this. How many moles of gas are in the original sample? Well, now I can just use a straight PV equals nRT, and I'm looking for N. But I know P, the original, I know my original volume, I know the universal gas constant, I know the temperature. Okay, so pressure. My original pressure was 550 millimeters of mercury. Okay. I don't know. I don't like working in millimeters of mercury. I like working in atmospheres. All right. So I would probably quick convert out of millimeters of mercury. All right. So I would say 1 ATM is 760 millimeters of mercury equals X over 550 millimeters of mercury. And it turns out that I have 0.724 atmospheres. You don't have to do that. You can work in millimeters of mercury. I gave you the universal gas constant for it, so it doesn't matter, right? But I don't know. I learned to work in atmospheres, so I tend to work in atmospheres. So now I can just say 0.724 atmospheres times my pressure, and now it has to be in liters because I'm using the universal gas constant, 0.250 liters. I want to know how many moles it is. Universal gas constant is 0.08206 liter.atmospheres mole K. And we are at 298 Kelvin. So it turns out that we have 7.40 times 10 to the minus third moles of gas. Now, just for fun, let's do a C part. The sample is an element and has a mass of 0.525 grams. What is the element? Well, I know moles and I know grams, so I can calculate GFM. Number of moles equals my given mass or my gram formula mass. Okay, so my moles was 7.40 times 10 to the minus third moles equals 0.525 grams all over x. Cross multiply. X ends up being 70.9 grams per mole. Well, now I have to go to the periodic table and figure out which gas it is. Okay. Chlorine, which is a diatomic, has a mass of 70.9 grams per mole. So this would be my gas. All right. So that's all I'm going to do for today. It was just a couple of quick examples of how to use the universal gas constant or the ideal gas law. You're going to be doing some practice with this stuff, and there's more that we're going to add to this eventually, or next class. All right. So go ahead and get some practice in, and that's where we'll end.